it is bounded. Okay, so unlike a simple attractor like fixed point or periodic attractor, strange attractor is we have fractal geometry. What is fractal geometry? It's actually the system exhibits self-similarity. So whenever you zoom in into that particular space, the outcome will be the same. So the structure will be the same. So that is what we call a fractal. In the next lecture, I will explain about fractal as well. Okay, and just now, I already mentioned strange attractor. Okay, it's too sensitive, right? Strange attractor exist in the system where deterministic equation produce a unpredictable behavior. Okay, so few characteristic of strange attractor. First is predicticity. Okay, I cannot touch. Okay, good. Okay, so whereby means that the trajectory will never repeat. Okay, we will never repeat. So we will not have a regular motion or periodic motion. The second one is fractal dimension. So whenever we have a strange attractor, we're going to have a fractal dimension. And this fractal dimension is not likely like 1D, one-dimensional, like a line. Also not like a 2D shape, or also will not like a 3D shape. Okay, so that is fractal dimension. And as we mentioned already, sensitivity to initial condition. So this strange attractor will be very sensitive to any initial condition. And boundedness means that the trajectory will confine into a finite region. It will be not go to diverge infinitely. And lastly is invariant measure. So the system that has a statistical regularity means that certain regions of the attractor are visited more frequently by trajectories forming to a probability distribution. So I think invariant measure has been discussed by Professor Lamberto in so many lectures here. So I'm not really go into that invariant measure. So because it's already covered by Professor Lamberto. Okay, so let's go to the mathematical structures and dynamics of chaos theory. I mean chaos equation. I will go for. Sorry. Before we go to the example, we go for the key point that we need to check. Okay, so for the first is fixed point and the stability analysis. Okay, so this is the foundation for understanding system behavior before chaos. So this is very important. So whenever I got the model, I got the system, the first thing that I need to check is the fixed points and to check their stability. So with this, whenever we got the result, then we can plot into the phase space and to find the Lyapunov exponent and also bifurcation. So this is the first important step that we have to do. Okay, and the stability and the fixed point is determined by the Jacobian matrix. I mentioned here there are 3 types of fixed point. So basically we have 7. We have 7 fixed point, 7 types of fixed point. So maybe we need to go one line by line for this fixed point because it indicates the behavior of the trajectories nearby the fixed point. So we need to know in this particular fixed point what is the outcome. In this particular fixed point, what is the outcome. So I need to go in detail. So let's go. We start with the first. Okay, let's go for the first one, whereby we have a stable fixed point. Okay, it's a stable fixed point. So in stable fixed point, we will find the eigenvalues, and these eigenvalues will determine our our result. So for the stable fixed point, our eigenvalues should be negative real part. Okay, negative real part. So in this stable fixed point, the trajectories near the fixed point will converge towards this fixed point, okay, without any oscillation. Okay, so that's why we call it as stable. Okay, so for the second one is reversed by this, which is we call it unstable. Unstable, and our eigenvalues would be positive real part. Okay, so this is, I think I write here, yes, we have these two, the one that I mentioned. So the the behavior would be, trajectories will be diverge, whereby we can say the behavior is unstable, and it will be repelling. Okay, so but that's still without oscillation. Okay, so next we go for, before I go to complex eigenvalues, okay, I move towards number 3. We call it as spiral. Okay, in this spiral we have two types. One is the spiral focus, and the other one is unstable spiral. The other one is unstable spiral. Okay, so we have stable spiral, and the second one is unstable. Oh, I'm so sorry with my handwriting, because Indian handwriting is very perfect and very nice. I really like the way, Indian handwriting. Mine will be very, very ugly, I would say. I don't know, because maybe your writing in Hindi or Tamil is very good, right? So, and difficult. So ours is not. So bear with that. Hopefully you can understand. Okay, yes. Okay. So we go for stable spiral. So stable spirals, whereby we got our eigenvalues is complex, complex conjugate with negative real part. Okay. So it's a complex numbers with positive real part. Sorry, negative real part. Okay, and it will be the otherwise for the unstable spiral, whereby the eigenvalues will be complex with positive real part. Okay, so the next one will be the complex eigenvalues. So these complex eigenvalues will say, this is actually complex because I already mentioned complex, right? So the other that I want to mention is actually saddle point. We call it saddle points. So this is very important, saddle point. So saddle points is actually indicates the chaotic behavior, whereby we also have the complex, but then with mixed eigenvalues. So saddle point means that we have mixed eigenvalues, we have positive and we have negative real part in both system. Okay. So in these trajectories, the fixed point along the stable direction for the negative will be stable. Will be converged, but then it will be diverged along the unstable direction for positive eigenvalues. So this is actually very important. Okay, it will be consist of two positive and negative it should be real part. Okay, positive and negative real part. Complex. Okay, I miss complex, right? Complex. It meets eigenvalues. It should be complex. And it consists of positive real and negative real. So this is saddle point. Okay, and lastly, we have center. Center means naturally stable, whereby the eigenvalues would be purely complex number. Okay, so that one we call it center. Center, purely complex eigenvalues. Okay, and lastly we will have saddle node. Okay, saddle node is also famous. Okay, saddle node means that it's like the number 4, but then saddle nodes, it should consist one eigenvalues that is 0. So that is the difference between 4 and 7. So one eigenvalues should be 0. So the other one can be positive and negative. No, I think because it's here. Yeah, I combined it into, so it will be 7. It will be 6. So this one will be 6. Yeah, thank you. Okay, so fixed point is very important. So you should be clear with what result you have, because normally when we want to simulate for chaos, we we want to check what parameter that makes the system chaotic. So we will do it try and error. Okay, so basically when I'm doing my PhD previously, I'm doing it try and error. So we put it values, parameter values, and then I will check the fixed point, and then I will run it for the Lyapunov exponent and also bifurcation. And then with these 3 completed, with the output that we want, so we can say our system is chaos. So no, this one is saddle fixed point. Yes, this one we call it saddle node fixed point. Okay. So that is a fixed point, and how we want to say about the stability. So the result, we can mention this result about the stability. Okay, and the second one we will move to bifurcation analysis. So there are 4 types of bifurcation. First is the saddle node bifurcation. Yes. Saddle node. Okay, so the behavior of the 0 eigenvalues indicates marginally stable or unstable direction. So it can be both stable and unstable direction. Okay, so
can you show us like with the face portrait and how
the face portrait. Okay, after this we will go for one example. We go for the example so you can see. Okay, we can view it. Okay, okay. So this is basically what this slide is actually the one that we're going to analyze one by one after this through example. Okay. Okay. So next we go for bifurcation. So there are 4 types. We have a saddle node bifurcation, intermittency, Hopf bifurcation. This is also important because this indicates the hallmark of chaos in that system. And then we have predict doubling cascade, where when this one happening will be chaos. Okay, and also we also need to check the limit cycle and the strange attractor. So why I make it versus, because this is 2 different things. Limit cycle is periodic oscillation, this is oscillation, but then strange attractor is something different. Okay, we are talking about the trajectories of the system. Okay, so for limit cycle, we can have predict motion, we can have the stability, and we can see the attractor whether it's a repelling. So if it is repelling, we call it this unstable. But then if the stable, you can see it is attractor. And then we will check the sensitivity of to the initial condition. So this one will be quantified by Lyapunov exponent, as I mentioned. Do you still remember the result for Lyapunov exponent? If you have positive Lyapunov exponent, indicates chaos. If negative Lyapunov exponent, stable. Okay, so that is good. Okay, so with that, whenever we check based on the parameter that we will input, so that will be our result, so we can see through it. Okay, and then also with the strange attractor, we should have a fractal geometry and self-similarity. So whenever we go, we cut it into small pieces, it will be actually from the same geometry as the whole. Okay, and fractal is actually they measure the complexity of the strange attractor. And invariant measure. So we in invariant measure, we actually explain the probability distribution of the states that the trajectory visit over time. So whenever the trajectory where it visit frequently, so that is what invariant measure will tell us. Okay, there are three important things for the invariant measure. I think you already go this one deeper for with Lamberto's. So to understand this is very fundamental, so that it can use for understanding chaos. So next, we try with Lorentz system. Okay, so this is a famous one, as I mentioned, because this is what Lorentz simplified. So actually, they have a much complex equation for weather prediction. So during 1963, Lorentz simplified into this particular dynamical equation. Okay, so there are three variables, or what we say, three state variables, and also three parameters. So basically, during that particular time, Lorentz thought this is very simple and deterministic equation. So he didn't think about so complex behavior that this system will be occurred. Okay, so we have a sigma, we have rho and beta. So sigma is Prandtl number, rho is related number, and B is actually a scale factor, or we call it geometric factor. Okay. So, this parameter that I'm written here, 10, 28, and 3/3, is a parameter whereby chaos behavior started. Okay, so after this point, the chaos behavior started. Okay, so we cannot solve this equation algebraically. We have to use numerically. So the famous method that we use to solve chaos equation is we use Runge-Kutta. Okay, and we have to use a very small time step so that we can get better accuracy. And this is what we call the way we iterate our system. So we need to iterate to get the solution. Okay, so I think this is the video, right? No. Yes. No. Okay, so if you can see over time, the value of x, y, z will change according the system. So at first, it looked like very nice. It looked like very nice, and then it will be appeared random. Will be appeared randomly, and then it will be goes to unpredictable. Okay, so you see now they are entering unpredictable and random behavior. So they will go like here and there randomly. So that is what we said. It is very sensitive to the initial condition. Okay, and in fact, even they will start go here and there, but then it still remain bounded. It's still in that butterfly shape. Even if we go start from here and then move here, it will start, you know, okay? So that's what we said. Lorentz system is very in chaotic behavior. With this, I mean, I run that one with this particular parameter. Okay, so let's go to try how we do the iteration. Okay, so let's try how we manage to do the iteration. I mean, yeah, we cannot solve it numerically. We have the eraser? Okay, okay, I see. Thank you. Oh, okay. It's too, I mean, okay. Okay, so okay. Okay, so we have the equation. Okay, when we talk about the chaos system, it should be in nonlinear, right? Remember? So we need to know the nonlinear term, and then it should be in a system. Okay, so then we can cooperate with chaos. So we have the sigma y minus z, and then y derivative we have x rho minus z minus y, and z is xy minus beta z. So how we want to iterate? Well, sorry, yeah. I think I said 1 minus 8, but then I writing xy minus z, right? Okay, so how we want to iterate? So let's say we are using this number for the parameter 10, 28, 8, and 8/3. So we will have x dot is equal to 28 y minus x. Or maybe I will just change it here, so I don't need to write it so many times. So this is 10, this is 28, and this is 8/3. Okay, so we're going to use this step for iteration. So let's say our time step is 0.01, and we use the initial condition as x equal to 1, y equal to 1, and z equal to 1. Okay, so when the initial condition 1, 1, and 1, you will have the time derivative x is 0. And then when you have y, will be 1, 28 minus 1 minus 1. So it will be 26, right? 26. And then it will be time derivative of z would be minus 5 by 3. Okay, so this is the first. And then we find the time step. We use the time step and we include in this formula. So we will have x1. Let's say this one is x null. So we will have x1 1 plus 0.01 into 0. So we will have 1. And then y, we will have 1 plus 0.01 into 26. And then this one we will get 1.06. And z, we will have 1 plus 0.01 negative 5/3. So we will get minus No, it's 0.983T. I have the answer. Yes, right? Yes. So this is what we are getting for the second iteration. 1, 1.26 and 0.9388. So we will do the same for the second iteration, whereby we use this number and we include in that particular same. So x2 would be 1 plus 0.01 into 1. So we will have 1.00, 1.10. Am I right? No. Oh, sorry. So this one is actually no. This is the second iteration. We will use no. Yes, supposedly 1.026. Where I'm missing something. For second one, oh, no. No, actually this is the time step. I didn't find yet this is the time step. I need to use this formula, so I didn't use it. So this is the time step only. So this is actually if I'm sorry. So I will include this time step into the equation. Okay, so we will have the first iteration 10 into 1. Sorry, y. Y is 26 minus with x. X is now is oh sorry, y now is 1.26 minus 1. Yes, correct. So this one would be 1.206 and y would be x is 1, 28 minus 0.9833. So this one we will have minus 1. No. So this one I will have 1.5, actually 1.76. There is a mistake there. So it's actually 1.5176. Okay? And then oh, okay, sorry. This one I miss y. So I miss y. So because z minus 1, y is 1.26. So the answer would be 1.5176. Okay, that is wrong a bit. Okay, and then z1 would be x is 1, y is 1.26 and minus 8/3. Z is 0.9833. 3. So this would be as indicate 0.9697. So so basically this is the way we iterate. So I think this is not Range-Kutta. Okay, this is only Euler method, just simple one, just to show how the iteration process. And as you can see, over time, the trajectories will be settled into a butterfly pattern. So is there any wrong calculation?
Like if we minus 1 from 30, set it to 27 minus 1.2, whatever we will take to.
This one? You are talking about this one? This one? This is wrong?
The first one is also not coming because it is coming something like it is 2.6. The first one is 2.6.
This one also not coming. 10 into 0.26. 10 into 1.26 is actually 2.6. So this is 2.6. Is it? Not 1.26. Okay. Oh yes, 2.6. Yeah. Okay. But then this one is also not coming, right? So this is actually 25.7567. Okay, maybe you calculate for me. So this one is so this is we get for the second iteration, and for the time step for the next one we will repeat the same one, which is we using this one. So we be x 2t plus s 1 now is 2.6 plus 0.01 into, so your dx dt now is, sorry, this is your x right? Yeah, which is 1, and then mine into 2.6, and then y also you will have the answer. What is that? So 1.026, and the second the same one will be for y. So y now is 1.26 plus 0.01 into your derivative is 25.7567. Okay, so you got it. So z would be plus z equal to z would be 0.9833 plus 0.01 into this one is 1.3621. So into 1.3621. So you can calculate. Yes, correct. Okay. So first we find, when we have the initial condition, we find the derivative, and then we calculate the time step, and then we will get the second derivative of not the second iteration of derivative, and then we do it for the second time step, and it will be repeatedly doing the same. Which one? Y1? 1.576. Okay, so it's coming, right? Okay, yeah, 167. Okay? 76, okay. 176. So this one is also coming, right? Okay. So this is the way whereby with the initial condition, we get the derivative, and then we calculate the time step, and then after the time step, we got the iteration for the derivative. And then we do the same for the second time step. Okay? So this is just how we iterate the system. Okay, this is just how we iterate the system. So next we move up to the important parts here. This one, it's not coming the same. 0.9697. Correct. 0.9969. Okay, so maybe. Maybe this one. Maybe this one is wrong. Because in my calculation, I got, no, I don't know, I got infraction. Minus something, yes, minus. Minus 1.3621. So, okay, just, okay, it's minus. So, I think it's coming. Okay, so basically this is actually, we not even think about it. That's why I also forgot, because we have the calculation now. Okay, so, but this is the way we iterate the system. Okay, so now, okay, this is important. So we need to find the fixed point, because the fixed point we need to calculate by ourselves. We cannot use, because it's easy, so we just calculate how we want to find the fixed point. So in Lorentz system, we have two fixed points. So you know how to find the fixed point? How we want to find the fixed point? Yeah, one. Can you tell me, or you want to do in front? Anyone? So what is the definition of the fixed point? S dot is equal to 0. Yeah. So fixed point, when the fixed point is actually whenever we got the derivative is equal to 0. So with this with this derivative, we just find the fixed point. So we have, for example, here, so we will have y equal to x for the first equation, and then x, this one is rho, right, just now, minus z minus y equal to 0. So now y is equal to x, so we can have minus x equal to 0. So x is equal to rho minus z minus 1 equal to 0. Am I right? 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 And then we use the third one, x y minus beta z equal to 0. So x square equal to b z, and then we can have this one, x equal to 0, rho minus z minus 1 equal to 0. So z is equal to rho minus 1, right? So we put it in here, x square equal to b rho minus 1. So x would be plus minus square root of beta rho minus 1. Is it? Am I right? Correct, right? So that's why my point is beta rho minus 1 plus minus s y equal to x. So we have s y equal to x, and then our z would be rho minus 1. So this would be our fixed point. So that's why I said we don't know the parameter. So you need to assume, because this Lorentz is very famous, so you can know the parameter whenever the system is chaos. But you need to think of when you have a system, you don't know what parameter that system will enter chaos. So this is why you need to do it. Try it. For me, for the fixed point, I will try it one by one. I will calculate the fixed point, and then I will check the Lyapunov exponent, also the bifurcation. Okay? So as I mentioned just now, we want to check the stability. So using stability, we need to use Jacobian metric. Okay, so and we have to find the eigenvalues. So do you know how to find the Jacobian metric, right? So we just find the derivative of each particular x, y, and z. Okay, so for Lorentz, our Jacobian would be negative sigma, sigma 0, rho minus z, negative 1, negative x, y, x, negative beta. Okay, so when you go for your simulation with your eigenvalues, so this is the result for your eigenvalues. I mean, this is also, I think this one also we can find it algebraically. Right, we can find it algebraically based on the Jacobian metric that we have here. For the fixed point 0, 0, 0, if I'm not mistaken. So let's say if our fixed point 0, 0, 0, so our Jacobian would be negative sigma, sigma 0, rho minus z, minus 1, minus x would be minus 1. Sorry, 0, because this is the fixed point 0, 0, 0. So we have two fixed points, right? Because we have x equal to 0 here. And then this is, we call it trivial fixed point. And this one, we call it non-trivial fixed point. So now we check for the trivial fixed point, 0, 0, 0. So our x will be 0, our y will be 0, our x will be 0, and minus beta. Second column, first column, second row. Okay, so this one is only row. Yeah, thank you. Because our z is 0, right? Okay, so we can find the eigenvalues. Whereby it would be negative sigma minus lambda, sigma 0, rho negative 1 minus lambda, rho 0, 0, negative beta minus lambda. So if you are using 3 by 3 metric, we will get sigma minus rho into 1 minus lambda, negative beta minus lambda, right? And minus sigma over, so rho into beta minus lambda. Okay, and Jacobian metric says the eigen is equal to 0. So we will find, I think we can factor negative beta minus lambda. So this one would be negative sigma minus lambda, negative 1 minus lambda, minus sigma rho equal to 0. Am I doing it correctly now? So I factored this one. So this one will be here, this one will be here. Correct, right? Okay. So next, so this one will be our first lambda, our first eigenvalue, whereby is equal to negative beta. Okay, and obviously it will be that one, right? Am I right? Yeah, you have to, what we call, expand and plug it into the equation of what we call, to find the roots. So supposedly, I think you can manage to get that one. Okay, so when you calculate you simulate, I mean using MATLAB, so you will have two eigenvalues that are negative. So I mean this eigenvalues is actually complex number. Okay, this is actually complex number. I forgot to write the value actually, and this indicates that stability in two direction. Okay, is because it is negative, so it is attracting. Okay, so you need to remember whenever the eigenvalue is negative, your behavior will be attracting. Okay, will be attracting. And then one eigenvalues is a complex eigenvalues, as I mentioned. Okay, is positive, so an instability occurs and the trajectories is actually repelling. Okay, and then yeah, we have a 0, 0, 0. It is a mixed eigenvalue. I mean, it's a mixed eigenvalues. It's a complex eigenvalues and mixed. So we call, as just now, the types of saddle point. The types of fixed point will be saddle point. Okay, and we can analyze that trajectories be nearby the fixed point. Our trivial fixed point will be attracted in two directions and repelling in one direction. So that's why our Lorentz, like this one, is attracting and then it's repelling. It's attracting and then repelling. Okay, and this is for non-trivial fixed point, whereby I use rho 28 because I'm using the chaos parameter with the same 10 for sigma and beta is 8/3. So this is the fixed point values when we substitute the values. Okay, so the eigenvalue that we get would be one is negative, complex negative. Okay, one value is a complex, which is it indicates stability. So if it's negative, means that it's attracting or repelling. This is my question. Is one eigenvalue is negative, is attracting or repelling? Attracting. Okay, so remember when it's negative, it is attracting. Okay, and then we have two eigenvalues with complex positive real part. Okay, so this one is pairing instability in the other two directions, so will be in other direction. So this one, the behavior will indicate oscillatory divergence. Okay, so we have one positive, and we have mixed actually, right? We have mixed negative and positive, so we still call it as saddle. Okay, and so trajectories will be spiral outward due this complex eigenvalues with positive, and will be some stability in one direction because the complex eigenvalues is negative real part. Okay, so this is the analysis that you have to do whenever you have the fixed point and you find the eigenvalues and you see what is the values of that eigenvalue. So this is the analysis whenever you have a system that you want to find the chaotic behavior. Okay, so I'm giving the summary. So we have two types of fixed point, one trivial, one non-trivial. So the trivial would be 0, 0, 0. We have three eigenvalues. Okay, and we need to talk about the stability condition. If rho is less than 1, we will have all the eigenvalues in the real part which is less than 0. So when it is less than 0, we can call it stable. Okay, and whenever we have rho greater than 1, we will have one eigenvalues with positive real part. So whenever rho greater than 1, we can call it as unstable. Okay, it will be inside the point. Okay, so for non-trivial case, so we have two complex conjugate eigenvalues and one real eigenvalues. So for the stability condition in the real part, we can say it conjugate, it converge and is stable. But then for increasing value of P, pre-critical here is a hallmark of chaos. I will explain later. So the real part will become greater than 0. So this part will be unstable when all real part, because we got the positive positive real part of eigenvalues. So this one will lead to oscillation and chaos. So it's still oscillation because this we are talking about P. I mean we are talking about P greater than one. So at first it will be started to oscillate, and then it will be go for chaos. Okay. So now we go for the bifurcation. So you see, at first this is a stable fixed point. It's a stable fixed point, and then it merged to the fixed point is unstable, so it come to the second fixed point, which is non-trivial fixed point. And so this is what I mentioned pre-critical, whereby this is the hallmark of chaos. After this part, everything will be chaos. Okay, so this is a bifurcation diagram to represent chaos. You can see how dense the points is there. Okay, so the same one that we're going to highlight here, because we don't know exactly, whenever you have a system, we don't know the value of parameters. So we need to check for all the parameters actually. So now for rho less than 1, we can have the trivial fixed point. So it is a stable condition, as you can see, it's a stable condition. And whenever rho equal to 1, so that trivial fixed point lost the stability. So it goes to saddle node, whereby the just now that we mentioned, when it's saddle point means that we have the complex eigenvalues with mixed real part. Okay, so the two non-trivial fixed point merge in this particular time, and whenever we have, when we reach to the point where P is equal to approximately equal to 24.74, so this hot bifurcation occurs. So this one, it leads to oscillation, and it's actually a hallmark of chaos. It's onset of chaos. So this is one of the important what we call analysis of chaos theory. So bifurcation is actually capture how small parameter changes and alter the system dynamics. Okay, so maybe I will ask why the non-trivial fixed point lost the stability up to this point, up to P, I mean rho greater than 1. How does the trivial fixed point lost the stability? Why? I mean, why the fixed point lost the stability? Okay, just now we have a few types of fixed point, right? So the first one is the stable fixed point. So its stable fixed point means we have a stable system. But then why the system goes to unstable? Because we have eigenvalues. Because the answer would be relate to the eigenvalues. So when we have the positive and negative eigenvalues, so it will be unstable. Okay? So whenever we talk about stabilities, we need to check the eigenvalues. So it back to eigenvalues. Okay. So next, we go for the limit cycle. So here I would like to share you how the different row will come up with a different phase. So at first I try with 5 and then 15, and then I goes for the hallmark of chaos, and then this one I goes for the 50, row 50. So you can see how dense and how the system goes. Okay, at the first one it just moving towards the fixed point. Okay, and then it goes for the oscillation, and then it goes for the chaotic behavior. Okay, and now here, this is also important for you to highlight the difference when you want to do the analysis, the limit cycle and also the strange attractor. So limit cycle means you have the oscillation, is a periodic motion, and for strange attractor would be non-periodic and the motion is chaotic, and the geometry also will be different. For limit cycle, it's very smooth and closed curve, but then it's not happen for the strange attractor. It will be fractal with self-similar structure. And then the stability for limit cycle is actually stable or unstable also. They attract and sometimes it repelling, but then for strange attractor is always attracting. Okay, and of course predictability, for limit cycle we can predict the motion, but not for strange attractor. And the dimensionality, it will be 1D curve in phase space, but it will be fractal dimension. And for example, we can have for limit cycle van der Poel oscillation. For the strange attractor, I think how many system I already touched? We have a Lorentz. Rosler I didn't mention any yet. So we have Lorentz. In the first lecture, I already talked about logistic map. And what else? In the fast way just now, Hannon map, if you can remember, Hannon map. Also with the Lorentz. Okay, so next, so we move to the sensitivity to initial condition. So I would say the same, actually, the same figure I give you in the first lecture, but then that one with animation. This one without the animation. So we have two initial condition. If I'm not mistaken, I put it for X, for first initial condition, 111, and the for second one is 1.001, Y is 1, Z is 1. So I just changed the value of X, 1.001 and 1. So this is the result. Okay, it's still in butterfly shape, but then for each point, it will be very, very vast difference. Okay, even we start in very small difference, which is 0.01, but then in particular, if you take another point over time, the result will be not the same. So that's why you can see it's still bounded, it still remain in the same, it's still confined in the region, but then for each output will be very, very totally different. That's why, as I mentioned just now, Lorentz, when they come out with the result, at first like same, and then it moved towards 1 decimal missing, and then 2 decimal missing. Towards the end, everything will be very different. Okay, and this one also we need to do, whereby we need to check the divergence of trajectories over time, which is the difference between two trajectories, okay, between 2 points. So when, for example, you have 1 point X for the first initial, and for the second initial, you take for the same value of X, we need to check how long they are diverged. So this is the divergence trajectory. So you need also to check how sensitive, actually we want to know how sensitive the system is. Okay, so next, how to calculate the Lyapunov exponent. Okay, so this is also important, how we want to measure the Lyapunov exponent. For this step, I'm giving you a method of, I think, 2 trajectory method, whereby I find the difference between 2 trajectory. So this is the way. First, we need to find, of course, we need to find the initial point, and then we need to solve, of course, and then the third one, we measure the distance between each trajectories, and then we use this formula to find the Lyapunov exponent. Okay, so basically this is the formula, the same formula that I showed in the first lecture, but then in the first lecture is exponent is in the other side. So this one we are looking for the exponent itself. Okay. And this one I plot the Lorentz using rho, the real number as the x-axis, and I find the Lyapunov exponent. Okay. So now maybe we can see. Yeah, we cannot. I mean, the value, whenever the value of negative, we will say the system is non-chaotic, or maybe we can say stable. Okay, the trajectories is converge. Okay, but then when it goes to positive, okay, you can see it started from here, but then this is started is a hallmark of chaos. It started to negative and to positive, so we can say the trajectories is diverge between each other, and that is what we call chaos. Okay, so yeah. Okay, now we move to the fractal. So fractal is actually a structure that exhibits self-similarity. It's actually the same as its own. Okay, whenever you zoom it, you will find the same structure. When you zoom it again, you will find the same structure. Okay, so and the fractal dimension is actually non-integer. Okay, as I mentioned, it's not 1D, it's not 2D, neither is not 3D. It lies in between. So it is non-integer, and it indicates how much space the structure fill in. Okay, and fractal in chaos theory, it helps us to analyze the complexity. Okay, so if you can see here, I plot the Lorentz attractor, and I take some of it, and if you can see, it is actually the same structure. Okay, so that's what we call fractal. So the geometry look like the same. Okay, now we move to invariant measure. I don't want to go deeper into this, but then I just want to highlight the figures. Okay, so for invariant measures, you want to see how much likely the attractor has been visited. Okay, has been visited. So in this green yellow line, higher probability that the region always spend more time there. Okay, and the blue region indicate that the trajectories visit not really frequent. Okay, so this is invariant measure, and I think that's all for Lorentz. So we covered already the fixed point, and we check the stability. You need to remember the eigenvalues is very important, and then we go for the bifurcation diagram. Okay, and then we need to know when you observe the bifurcation diagram, you need to know the hallmark of chaos. So that is very important. And the third one, we go for the limit cycle and strange attractor. Okay, we need to check the phase space that you are drawing. Is this like predictabling or is like chaotic? So that would be in limit cycle and strange attractor. The fourth one, we go for the Lyapunov exponent, whereby Lyapunov exponent giving us the sensitivity of the initial condition. And the fifth one, we go for the fractal. Okay, fractals is just easy, but by looking also we can see it is it is a copy, or we can say a copy of the original one. And lastly, I touch just a surface touch of invariant measure. Also, I can share you how to find if you need, or maybe you know already during the tutorial with Professor Lamberto how to write a code for invariant measure. But I can provide for, maybe if you have time for after this lecture tutorial, maybe we can go for, if you want, for invariant measure code. Okay, I think that's all for today's lecture. We go for the tutorial. Am I correct in the correct time? Okay, so basically I have more for Lawrence, but then I can see because I don't want to, get delay. So this one maybe we can talk later if you have time. Let's see, because this is also interesting to go Lawrence system. So okay, we will try to go in depth for Lawrence. For Rosler. Okay, so is it here for the in the lab? Okay, so we need to move.
No need to walk too much. Just one room after.
Okay. Okay. So I didn't have time to ask just now. Say any question from the floor before we stop and go to the another. To the lab. Okay. So.
How much time you need? Because you are fast. We are sitting in the
Yeah, that's why I don't know. Oh, for the tutorial. No, it's okay. I just need drink. Water.